In the Microdynamic Systems Laboratory at the Robotics Institute of Carnegie Mellon University, we have been working on developing visual haptic interfaces for virtual environments. Correct visual haptic registration is very important, especially when the system is used for visuomotor skill training. We have proposed a "what you see is what you feel" concept, or WYSIWYF for short, which ensures correct visual haptic registration. Our first prototype of WYSIWYF display consists of a Puma 560, a 6 degrees of freedom industrial robot for the haptic interface, and a color liquid crystal display for the visual interface. A color CCD camera is attached to the back plane of the display, and this camera display system is mounted on a movable stand. A 6-axis force-torque sensor is attached to the robot, as well as 4 small incandescent lamps, which are used as markers for vision-based pose estimation. In order to apply the chroma keying technique, the robot arm and the working environment are covered by blue cloths. The first step of WYSIWYF display is vision-based tracking. The original video image is captured by a CCD camera. By tracking the markers attached to the robot and reading joint sensor information, one can estimate the pose of the camera display system with respect to the fixed environment. Using the estimated pose and the joint angles of the robot, one can render the virtual object in the background image of the virtual environment so that the virtual object is registered to the haptic device and the background is registered to the fixed environment. This sequence demonstrates how well the virtual cube is registered to the haptic device while the user moves the camera display system around. The virtual cube image is overlaid on top of the original video image. The markers also could be placed on the fixed environment. Unlike the augmented reality case, however, what the user can see is only the virtual environment scene. The next step is video keying. Instead of rendering a synthetic polygonal hand, we use the real user's hand image captured by the same camera as used for tracking. The chroma keying technique allows us to extract the user's hand from the blue background. The extracted hand image is pasted on the virtual scene to make the final image displayed to the user. Since the virtual cube is well registered to the haptic device, the user can touch the actual knob of the haptic device exactly where he reaches his hand to the knob of the virtual cube in the displayed image. Using the live user's hand image allows us to eliminate a data glove-like sensing device. The third step is physically based simulation. A non-penetrating simulation algorithm is implemented to control the haptic device. The user's applied force is measured by the force-torque sensor. Static constraint forces and collision impulses are calculated, and the resultant motion of the virtual object is obtained by solving Newton-Euler equations. The system provides correct visual haptic registration. The user can see the virtual world through the LCD panel as though looking through a window. Our approach is classified as an encountered type haptic display. When the user tries to reach for the virtual object, he can see his own hand in the display. When his hand reaches the virtual object, his hand can actually encounter the haptic device and get the haptic sensation through that device. What the user can see is exactly what he can feel, therefore the WYSIWYF situation is realized. One limitation of this approach is that with the currently available technique, the accessible portion for the user is limited. In this case, the user can encounter only the knob, one face, and the surrounding 4 edges of the cube. The user is now manipulating a virtual cube and moving the camera display system at the same time. The user can disable the tracking functionality and fix the camera display location as he likes. In another example, please note that the ball is a virtual image, but the racket is a real image. This is what the user is actually doing. This example demonstrates that the user can interact with the virtual environment not only with his own hand, but also with other real tools. One potential application of this system is for the training of visual motor skills, such as in medical operations. This sequence shows a simple example of training. The user is trying to follow the pre-recorded motion of the expert. A weak position servo can guide the user to the reference motion. Unlike just watching a video, the trainee can feel the reaction forces while following the reference motion. A WYSIWYF display provides more realistic visual haptic sensations than a conventional visual haptic interface configuration. We will be investigating the use of a head-mounted display, which would realize more realistic WYSIWYF situations than an LCD panel.